So it was in section 5.3 where we introduced the recursive sequences. And we want to continue with this, but we want to look at just what we call linear homogeneous recursive sequences, or we can call them recurrence relations. Sometimes you hear them called recurrence relations. So let's give a definition. We're going to define what is a linear homogeneous recurrence relation. So definition. A linear homogeneous This is actually the British pronunciation right here, British pronunciation. In the US, some people say homogeneous. In the UK, they say homogeneous. And many of my past faculty mentors were British. So I've always picked up saying homogeneous. So linear homogeneous recurrence. Relation of degree k that's what we're defining, a linear homogeneous recurrence relation of degree k with constant coefficients, Yeah, so we're defining this whole entire term right now. Is a recursive sequence that may be written in the form AN equals C1 AN minus 1 plus C2 AN minus 2 plus so on and so forth. CK A sub n minus k. So this here is the form of a linear homogeneous recurrence relation of degree k with constant coefficients. So just some notes we want to add here. Notes. The first note I want to make is that linear, this word linear, this is indicating that the powers of the AJs are all 1. Linear indicates the powers of the AJs are 1. Yeah, so each of these terms here, call these the AJs. The power on each of those is 1, right? We don't have any squares, we don't have any cubes, we don't have any fractional powers, nothing like that. Now, second note we can make, let's put that in blue. Note 2, when you use the word homogeneous, or homogeneous if you want to use that version of the word. Ooh, I misspelled it. homogeneous this indicates there are only terms with the AJs, those red AJs. There are only terms with the AJs. So it means you don't have any additional terms. So when we go here and we look at these guys, these are the only terms, right? You have what? In this one you'd have k distinct terms, right? an minus 1, an minus 2, an minus k. And some of those have coefficients, but yeah, you don't have any extra terms. You don't have any extra terms, so you don't have like a plus n at the end, or plus n squared or something like that. Right. So let's give some examples. See if we can classify. Let me call these maybe exercises. Exercises. Determine which are linear, homogeneous, recurrence relations, with constant coefficients. All right, so here's a number 1. Also find the degree. Also find the degree. So number 1, we have a sub n equals 3 a sub n minus 2. So this is definitely linear, right? So when you look at your AJs, so we have an and an minus 2. Those have a power of 1. This is linear. This is homogeneous because the only terms that are showing up are an and the an minus 2 type term. We don't have like a plus n or a plus n squared, so it's homogeneous. It's a recurrence relation. It has constant coefficients. Right, if you look at your coefficients, you have a 1 here and a 3 here. And the degree is equal to, in this case, the degree is 2. So if you look here, you have an equals 3 times an minus 2. So this number right here, that's called the degree. The degree is 2 here. So this recurrence relation is linear, homogeneous, has constant coefficients, and has a degree of 2. Let's do number 2. Number 2. We have, what do we have? an is equal to, how about an minus 2 plus 3an minus 4 plus 5an minus 6 plus n squared plus 1. So this is linear, first of all. So when you look at your AJs, the AJs, the AJs, the power on each of those is 1, right? You can imagine a power of 1 here, a power of 1 here, a power of 1 here, a power of 1 here. So the AJs have powers of 1, so it's linear. But it's not homogeneous, and the reason it's not homogeneous is because you just don't have these AJ terms involved. You have something else here. On the end, you have an n squared plus 1. So it's not homogeneous. Not homogeneous. I'll just draw an arrow there. Constant coefficients, yeah. Constant coefficients. So that's when we're looking in front of the AJs. We have a 1 here, right? We have a 1 here. We have a 3 here. We have a 5 here. So we have constant coefficients. We don't have any varying coefficients. No, like n's or anything like that. And the degree here is going to be 6. 6. Why 6? Well, when you look at the AJs, this one counts all the way down to an minus 6 right here. So the degree is going to be 6. So we have a linear recurrence relation, constant coefficients of degree 6, but it's not homogeneous. Let me scroll a little bit more. Let's do a third example. So here I'm going to do an is 4an minus 1 plus 3an minus 2 quantity squared plus 2an minus 3 cubed plus an minus 4 to the 4th power. So notice this one's not linear. Why is it not linear? Because the exponents. So when you look at your AJs, I'm going to call these the AJs, you have exponents besides 1, right? You have 2, 3, 4. So it's not linear. It's homogeneous. Why is it homogeneous? Because the only terms that are involved are the AJ terms. Or we don't have something on the end like a constant like 5, or we don't have something like n squared or n factorial or anything. So it's homogeneous. It has constant coefficients. You look at the coefficients, they're what? 1, 4, 3, 3, 2, 1. So constant coefficients. And the degree here of this recurrence relation is 4. 4, so we have what? N minus 1, n minus 2, n minus 3, n minus 4, so 4 is the degree. So we have a recurrence relation that's not linear, but it is homogeneous and has constant coefficients, and it's of degree 4. Let's do one more example. Number 4. Say you have a sub n is defined to be n times a sub n minus 1 plus n squared times a sub n minus 2 plus n cubed a sub n minus 3 plus n to the 8th power a sub n minus 8. So let's say you had a recurrence relation like that. This would be linear. If you look at the a sub j's, It'd be like an minus 1, an minus 2, an minus 3, an minus 8. They all have a power of 1 on them, right? 1, 1, 1, 1, 1. So it's linear. It is homogeneous because the only terms are these AJs. We don't have any extra terms like constant on the end or some kind of what you might call a variable expression on the end. So it's homogeneous. But it doesn't have constant coefficients, right? If you look at the coefficients, some of these coefficients at least, they're not all constants. So one is constant in front of the and, but the others are not. So non-constant coefficients present themselves. So we're going to write non-constant coefficients. And here we're talking about degree of 8. Degree is 8. Why? If you look at n minus 1, n minus 2, n minus 3, it goes all the way down to n minus 8. So there's your degree. So we have a recurrence relation that's linear and homogeneous, but we have non-constant coefficients. And our degree is 8. So basically what we're going to be doing, we're going to be learning how to solve only linear homogeneous recurrence relations with constant coefficients of degree k in general. So we'll be doing that in this section.